It's a pretty simple list of objectives for this particular subject because we're just going to be starting in. So the goal is to be able to apply the rules of Lewis dot structures to simple molecules. That's it. That's for this segment. Okay, so how to draw Lewis dot structures. We started talking about the idea of Lewis dot structures where you have lines representing bonds that have 2 electrons in them and then just dots representing the other valence electrons. Only the valence electrons are represented. So we count the number of total valence electrons. That's what we start out with. How many electrons are available for bonding? Draw lines to represent bonds where you're sharing. First of all, you got to start off connecting the atoms that you have. And subtract the number of valence electrons used for bonding from the total atom. Use up as many of these extra atoms as electrons as you can around the periphery atoms. And if there's leftover electrons in the right place in the periodic table, use an expanded octet. We'll get into that later. We won't get to that rule yet. If there's not enough electrons, use multiple bonds. If there's a deficiency of electrons, then 2 atoms can share electrons. So let's actually put these rules into practice. Okay, so we'll start with something pretty simple like ammonia. So we have 5 valence electrons for the nitrogen plus 3 valence electrons from the 3 hydrogens, which gives us a total of 8 electrons. So let's draw this. N, H, H. And obviously if you have hydrogens, the nitrogen has to be in the middle because the hydrogens can only bond to one other thing. So, so we have 8 electrons and there's 6 electrons in bonds, leaving 2 electrons over for a lone pair. And as we can see, nitrogen is actually short a pair of electrons to form a lone pair. So there we go. That's the electron dot diagram. We expect that H is bonded to the nitrogen is bonded to 3 hydrogens, but then there's 2 electrons left over that are not involved in bonds. Okay, carbon dioxide. So the question here is what's in the middle? Is it one of the oxygens? Is it one of the carbons? And generally, if you have an atom composed of nonmetals, that you'll see that the least electronegative atom is most stable in the center. So generally what we see, oxygen is fairly electronegative, so what we'd expect is that carbon would be in the center. So we have carbon here, and we start out OO. Okay, we've got carbon in the center, surrounded by the 2 oxygens, and we'll come back to that exactly how one can see that later when we talk about formal charge. But let's, for now, we'll just put the oxygen in the center. The total number of electrons, 4 valence electrons plus 2 times 6 valence electrons, so that's a total of 16 valence electrons. So you got 16 electrons, of which we only have 4 electrons in bonds. So that leaves 12 electrons left over. So let's see, we could put 6 on each side, and now each oxygen has 3 lone pairs. So that has a full octet, but we notice that carbon does not. Carbon is definitely way short of an octet. It only has 4 electrons around. So what we could do is each oxygen could share a pair of its electrons. So let's erase those there. Could share a pair of its electrons and form a double bond with C. So now we have what's the total number of electrons. We have 8 electrons in lone pairs. We have 4 bonds, so 8 electrons in bonds for a total of 16 electrons. We have 16 electrons, which is the total number of valence electrons anyway. So the way that the Lewis structure we'd have for this ends up corresponding pretty well if you deal with this at a much higher level of theory, is that there's a carbon with with double bonds with each of 2 oxygens, and they have 2 pairs of electrons each that are not involved in bonding. So that would be carbon dioxide. Nitrite ion, how do we deal with the number of valence electrons here? Well, there's going to be 5 plus 18, 3 times 6 from the oxygen, plus 1. There's 1 more electron there, so there's 24 electrons total. Nitrogen is the least electronegative, so that's in the middle. NO, and then for a Lewis structure, we draw a minus around it to represent that there's a total negative charge. So we have 24 electrons, minus 6 electrons in bonds, and so there's 18 electrons left over. We start by sharing them equally along the periphery. So that satisfies the octet rule of everything but the nitrogen. There's no more electrons left over to put like in a lone pair on the nitrogen. So the only way that we can keep the same number of electrons and still get nitrogen to have a complete octet is to erase one of these and draw a double bond there. And now let's just double check. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 electrons in lone pairs and 4 bonds, 8 electrons, 24 electrons. Now you might ask, well, how did you know to put the double bond in that oxygen? And we'll get to that later. One thing to notice for now is that, you know, they're all equivalent oxygens. So it doesn't really matter which one we put it on, and we'll dig a little deeper into that later on. Okay, so that's a few simple Lewis structures. Let's do some more. All right, methanol. So methanol, we don't have the bonding explained entirely, but we'll just, I'll just reason what it probably is. So the carbon is the most electropositive, the least electronegative. It's in the middle, so it's going to bond to one of the O. We know that carbon can generally forms 4 bonds. So this is the most likely arrangement of C3OH. It is the right arrangement. Let's total up the number of valence electrons. We have a total of 4 for the carbon, 4 plus 4 for the hydrogens plus 6 for a total of 14 electrons. And we can see we've got 1, 2, 3, 4, 5 bonds already. So 10E, that gives us 4 electrons left over to place in lone pairs. Oxygen is missing 2 lone pairs. So now once we put those 2 lone pairs in oxygen, we can see actually we've used up all 14 electrons. We have used up all 14 electrons. We have everything has a full octet except for, you know, the hydrogens, which all have 1 bond. They have a full doublet. And so yeah, that's the Lewis structure for methanol. Ammonium. Okay, so how many electrons are there? There's 5 plus 4, and then minus 1 because there's 1 less electron because it's an ion. So we've got N, H, 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 H plus, and that's 8 valence electrons. But guess what? We've got 4 bonds, and so that accounts for all the electrons. Nitrogen has a full octet. Hydrogens are all double. We're set. We don't need to draw any lone pairs or double bonds. That covers everything. Okay, C2H2, number of electrons is 2 times 4, 2 carbons, 2 times 1, for a total of 10 electrons. The carbons will be in the middle, and they'll each be bonded to H. So 10 electrons. Let's draw this over here so we can read it over here. Okay. HCH, and so we have 6, we've drawn 3 bonds, 6 electrons to bonds, that's 4 electrons left over. Well, you know, we could give each of them a lone pair, but that accounts for all electrons. We have 10 valence electrons there, but they're certainly not very happy. We don't have a full octet. But what we could do is just take these 2 electrons and turn them into a bond. Okay, that's a little better. But they still don't have, one of them has actually one has more than a full octet. So that one needs to have less electrons. So if we take these 2 there and actually share those, aha, now we've got 5 bonds. So there's 5 bonds, that counts for 10 valence electrons total. And now each carbon has 4 bonds, so it's sharing 8 electrons, so we're satisfying the octet there. So in this case, it would suggest that we have a triple bond between the carbon. That's the only way that we can actually satisfy the octet rule, given the number of valence electrons we have accessible. Okay, so that would be the Lewis structure there.